Good afternoon, this is Schweitzer. We're doing a little video here on how we go about taking concentrations of different reactants and reactions and coming up with a rate law. So let's quickly review what is a rate law again. I have an example here where I'm going to use this guy and come up with a rate law for it. So the rate would be the initial rate. We just usually put rate here, but initial rate would be a good thing to have there, equals the K value times the concentration of both reactants. I don't know what the orders are, so unknown value, and then times O2, which also would be an unknown value. This would be as close to our rate law that we can get. So what does this rate law allow us to do? Well, it says allows us to determine with these orders the initial rate. So it's a model. Okay, so let's review what that is. So zero order is one where if your rate equals a K and the concentration of unknown substance or X or reactant is 0, then no matter what we do with this thing to the 0 power is just 1. And therefore there is no change. Okay. If you're something that's first order, then it would be rate equals the K times concentration of the reactant to the first power, then it's proportional change. Meaning that whatever I do to this guy will also happen to this guy. And of course, if I have a second order, then I'm looking at something where, okay, the rate equals the concentration, let's say K value, times the concentration of X squared. So in this case, it's causing a squaring. So if I were to hypothetically raise this, double this thing, then it's going to be 4 times. If I take it and I multiply times 3, well, then it would be 9 times as fast. Keep in mind, all of these things are done by interactions at the molecular level, which is also on this quiz, typically. Alright, so let's try an example how this works. First things first, we have 4 trials. I separate this one a little bit, but this one doesn't have a rate. So remember, our overall main idea here is to be able to take some concentrations and find a rate, initial rate at least. In this case, what are we tracking here? So we're tracking, in this case, something. It doesn't always say. But they could lots of times say we're tracking the production of, let's say, NOCl4, so or whatever. That's a little sloppy. Get towards the end of my marker. Okay, let's track it. Let's just say it's tracking the chlorine. Okay, so you pay attention. Sometimes they have that on there, and they'll ask questions about that. So either way, how does this work? Well, I'm looking to see that if I change my concentration, how does it affect my rate? So the first thing I want to do is write out the rate law. So the rate law equals the K value times the concentration of NO times the concentration of the chlorine. I just don't know what these guys are. So what I do is I find some trials, and I pick out some trials that work for me, meaning that this isn't going to change at all. So any change in the chlorine will be the what's responsible for the change in the rate. This guy, and I literally draw right on it, I put a little number, arrow, and it goes times 2. And what did this one do? It went times, you could divide this by that guy if you want, times 4. What happens here? 2 to 4, times 2. Alright, 2 and 2, that's just a first order. So the chlorine is first order. That means this guy, get rid of the question mark, put the 1 in there. Alright. Now we got to pick out trials that work for the nitrogen monoxide. 1 and 3 works great because the chlorine's not changing. Right? So in this case, this guy is going to a times 2. And what's happening to this one? In the same direction, just draw your same arrow to see what happens. Times 4. Okay, and how do I get that 4? Well, I just 9 and 2 divide the 2 out. Right? As long as all the powers are the same, then you don't got to worry about it. But either way, divide those out, you get 4. So 4 and 2, that's a second order. Alright, other than that, other types of questions. Okay, typical things they ask here is, once you have the rate law, how do you determine K in its units? Okay, so my rate law is the rate equals K, the concentration of the NO squared, concentration of the Cl to the first. And I want to solve for K. So I'm going to take my rate divided by my concentration of NO squared, concentration of chlorine first, equals my K value. Pick out a trial. It doesn't matter which trial you pick, but in the end, you get a slight variation, but it's somewhat close. Just show your work. Plug all your values in, and then we have that. So, go ahead and do that. Do for trial 1. And you'll see, all right, in this case, I have the work below here, but the rate is going to be 2.27 e to the negative 5th divided by 0.0125 squared times 0.225, and you're going to get first, and this is going to give my K value. And if you trust my math here, it's going to be 0.645, and we want some, you almost always ask for these units. I'm not quite sure exactly why, but the units on here. So that's the answer, and they're going to have another point just for the units. So how do we get the units on this thing? Well, let's go ahead and let's try this out. This answer equals K, but the units also equal K, unit-wise. Let's put our units in here. It's moles per liter per second for the rate. So moles per liter per second. That's that guy. And this guy is moles per liter, but it's moles per liter squared and moles per liter to the first. Let's condense that stuff. So it's going to be moles per liter per second divided by moles cubed over liters cubed. So this gives both of these a square, and then put them together, and that's what we get. Now, the last conversion we have here is going to bring us to this. So to put this together, whenever you're dividing a fraction, we multiply by the reciprocal. So let's do it. Moles per liter per second times liters cubed over moles cubed. The moles cancels, and I'm down to a 2. The liters cancels, and I'm down to a 2. And what's left over is liters squared over moles squared seconds. And that's my units. Seems a little complicated, but really it's just condensing units and putting them together. Once you got it, you're good. What's my overall order? Well, it's second order referring relative to the NO, first order relative to the chlorine, third order overall. Okay, just so you know. That's how it works. The rest of these problems, you'll find that they're just a matter of practicing a few things. Now, the last one here, I'm going ahead and I'm putting in to find my unknown rate. Keep in mind, the whole point of this thing is to find my rate of a reaction, initial rate. So, I'm going to take my rate law. The rate equals my K value, the concentration of my NO squared, concentration of chlorine. Okay, the first. If you give me all these things, I can plug it in and solve for my rate. And that's what we're going to do. So, experiment 4 talks about this. It says, well, it gives this guy as being, and this guy, all the values are given below here, here, and here. Plug them all in and solve for your correlating rate. This, of course, is in moles per liter per second. Okay. All right, next one. All right, so let's walk through this and see how it works. So I want to find my rate law. So my rate law, to start out, again, you can pause this video and try it. I have one more example coming yet, so if you still need to work with me, you can, but you should be trying to push yourself onto your own. All right, so the rate equals K value, both my reactants, concentration of NO, concentration of H2. I'm trying to figure these guys out. Let's look at our stuff here. Holding constant, okay, this one's times 2. And this one is, in this case, looks like about times 4. So this guy here is going to be second order. I just have to write right there. And then this one is holding constant right here. This guy is times 2, and this guy is times 2. All right. In that case, this guy is first order. So we can rewrite this guy out here. I'm just going to erase this a little bit. and put in my appropriate 2 and 1. Now let's go ahead and solve for our rate, K. So divide out the rate divided by the concentration of NO squared, concentration of H2 to the first, and plug the values in. I just take the first trial, but you could take anyone you want. 1.3 e to the negative fifth divided by the concentration of NO, which is 5.0 e to the negative third squared times the concentration of 2.0 e to the negative third, and this is going to be the first. And I'm assuming you can do this math on your own. Okay? Let's go to the units. Let's just plug our units in right away. I have, looks like, moles per liter per second divided by, and this is going to be very similar to the last one we just did. Moles cubed divided by liters cubed. And we're going to get the same thing, which is going to be multiplying moles per liter per second times reciprocal liters cubed over moles cubed. This is going to give me, canceling out, liters squared over seconds and moles squared. Alright, pause the video, give this one a try. Alright, let's walk through. This looks kind of scary, but you got to pick out some numbers. You don't need all the data, but the rate law equals the K value times the concentration of the NO times the concentration of the O2. Alright, so what do we got here? Let's pick through some data. Find one where 1's held constant, a lot of 0.2's here, and where 1 changes. Now this guy goes times 2, so what is this guy? It looks like that also is times 2. Just glancing at it. So this guy here is first order. Alright, so now we got to find one where this guy holds constant. Well, we have a situation here where it's 0.04, 0.01, and 0.2, 0.02, so we could use these two, but I'm going to use these ones. In this case, these are held constant, and this one doubles. It's easy enough for me. And it's going from here to here. And that, once again, looks like a 4. So we have some common ones here. We have first order and we have second order. 2 and 4. Not always the case. Sometimes we have 0, sometimes we have 1s, whatever. This guy's a 2, this guy's a 1. At that point, we're going to plug in our values here to get the K value. So we're going to just solve it in here. We got 0.028 equals my K value, concentration of 0.02 squared, concentration of 0.01 first. Put this all together, divide it out, and you get your K value. I'm assuming you can do that math on your own. My units are also very same as the last ones, unfortunately, but it's just going to be the same process. So it's moles per liter per second equals my K, and then moles per liter squared times moles per liter first. This is going to give me K moles cubed over liters cubed equals moles per liter per second. Move those over, and you're going to get liters cubed over moles cubed. A little different way of looking at it. And of course, these are going to cancel, these are going to cancel, and we get a very familiar, at least for this particular presentation, of liters squared over moles squared per seconds. By all means, not the most common thing you have here. Now, if we want to figure out anything else about this, this is my last slide here. Other common questions were, if we're tracking here, let's say we're tracking the concentration of NO, then this common question might be like, okay, what is the rate of disappearance or appearance of something else? So if I want to know what's the rate of appearance of the O2 or disappearance of O2 in the first trial, I would do 0.028, and this would be of the, let's just say this is of the NO, then this is the rate of the NO. I would want to get rid of the NO and go to the O2 and then say 2 to 1 ratio, just using a stoichiometric ratio, jump from here to here, and you get your answer, which is 0.014, and that would be moles per liter per second. And that would be the O2 disappearance. Jump from here to here. That's a common question. Other than that, I don't see a whole lot else going on here, and thank you very much.